Welcome friends. By now you are familiar with the dynamics of the aircraft and the dynamic stability. In today's lecture, we will study the Routh stability criterion and the Routh array. Before we proceed for the Routh stability criterion, let us understand why this method was developed and how this is useful for us. You know, if we have a system with the transfer function f of s is equal to n of s by d of s, and if I equate this d of s with the 0, this I call the characteristic equation of the transfer function, and the roots of this equation are known as the poles of the transfer function. For a system to be stable, the poles of this transfer function must lie in the left half of the S plane. Suppose I have a transfer function having first order characteristic equation 1 by s plus a. In this case, my characteristic equation will be s plus a is equal to 0, and the pole will be s is equal to minus a. If I take the Laplace inverse of this transfer function, suppose this is my f of s, then the f of t will be e to the power minus a t, and if I plot it, it will be something like this. This is the t and this is my f of t. As the time tends to infinity, the response will die out, and that is why our system is stable. Let us see more examples. Let me write on the board. So, if my pole is at minus a, in time domain the f of t will be e to the power minus a t, and response will be like this. If my transfer function is 1 by s plus a to the power 2, in this case I will have two poles at the s is equal to minus a, and its inverse Laplace will give us the f of t, t e to the power minus a t u t, and it will look like this. In this case also the system is stable. If my system is 1 by s plus a whole square plus b square, in that case I have two poles in the left half, two complex poles, they are complex conjugate, and in this case my time domain equation will be e to the power minus a t sin u t, and I will get the response like this. For 1 by s, I have one pole at the origin, the response is u of t, and it will look like this. In this case, the system is marginally stable, because it is not tending to 0 and it is not diverging also, that is why it is marginally stable. If I have the transfer function 1 by s square plus a square, in this case I have two complex conjugate poles and they are on the imaginary axis. In time domain it will be sin a t u t, and it will oscillate between two finite values, and we call the system is marginally stable. If my transfer function is 1 by s square, in this case there will be a double pole at the origin, and my response will be t u t, it will be diverging and the system is unstable. For 1 by s square plus a square whole square, in this case there are two double poles on the imaginary axis, and my response will be t sin a t u t, and it will be a sinusoidal wave which is increasing its magnitude, and this will also be unstable. If I have a transfer function 1 by s minus a, in this case my pole will be at s is equal to a, and in this case it will be e to the power a t u t, and this will diverge with the time and the system is unstable. For 1 by s minus a whole square, in this case I have two poles at s is equal to a, and it will diverge faster than previous one, and this will also be unstable. For 1 by s minus a whole square plus b square, there will be two poles in the right half in complex conjugate, and it will be e to the power a t sin b t, and it will be unstable. So, one message is clear: if the pole is in the right half, the system will be unstable, and if there is double pole on the imaginary axis, in that case also the system is unstable. In this example, and for this transfer function also, the t sin a t, and the system is unstable. But if I have two poles on the imaginary axis at different locations in complex conjugate, in this case I will get, for individual pair I will get two sinusoidal waves of different magnitude, and the resultant will be the superposition of both, and the system will be marginally stable. So, if there is pole in the right half, the system is unstable. Even if I have a bigger transfer function, suppose I have a transfer function something like this, 1 by s plus a into s plus b to s plus s square plus c s plus d, something like this, and s minus e. In this case, I will have poles like at minus a, minus b, and suppose in this case I will get one complex conjugate and one pole in the right half. If I see its a response for these poles s is equal to minus a and s is equal to minus b, I will get this decaying exponential. For that also I will get one decaying exponential for the second one. For this complex conjugate I will get some decaying sinusoid. You see, the poles which are in the left side, the responses due to them are decaying with the time, and as t tends to infinity they will die out. But the response due to this pole, I will get an exponential which will be building with the time, and as the time tends to infinity this will also become infinity, and that is why the system will be unstable. So, it does not matter how many poles are in the left half, even a single pole is in the right half, the system will be unstable. If I have characteristic equation up to second or third order or maximum up to 4 order, it is easy to find the roots of the characteristic equation or the poles, but it becomes a tedious task to determine the poles of the transfer function if I have characteristic equation of higher order 5 or 6 or 7, and in this case the Routh stability criteria is used, and this converts this tedious task into a simple task. Suppose my characteristic equation is s to the power n s to the power n minus 1 s to the power n minus 1 a1 plus s to the power n minus 2 a2 plus something plus an is equal to 0. The all coefficients of the s must be positive or must have the similar sign. Even they are all negative, in that case we can take minus 1 negative and all will come positive. So, it does not matter, in the case of stability it does not matter whether they are positive or negative, they all must have the same sign. If there is any sign change in the characteristic equation, the system will be unstable, and it is quite obvious, because if I have s minus a, s minus b, or something like that. If there is any pole having negative sign, it will reflect a negative sign in the characteristic equation. This means there is one pole, at least there is one pole in the right half. So, the first criteria of the Routh stability is the all coefficients of the characteristic equation must have similar sign. The second criteria, even my all coefficients are positive, there may be both possibilities. The pole may lie in the left half or may lie in the right half also. And to check this, we use the Routh array. See this example. If I have a transfer function like 1 by s to the power 4 plus 2s cube plus 3s square plus 10s plus 8. In this case, the roots of this characteristic equation, if I write this as a characteristic equation, the roots are 0.5 plus minus I 1.93 minus 2 and minus 1. Here my all coefficients are positive, still I have this pair which is in the right half of the S plane. If I plot it, I will get this pair here, somewhere here, and one pole here and one pole here. So, even my all coefficients are positive, there may or they may not be the roots in the right half of the S plane. For this, we use the Routh array to determine whether any pole is lying in the right half or not. And let us understand this Routh array with examples. In our first example, suppose my characteristic equation is s to the power 4 plus 8s cube plus 18s square plus 16s plus 4 is equal to 0. First of all, the all coefficients must be positive or all coefficients must be negative, must have the same sign, and the first criteria is satisfied. So, to construct the Routh array, we write the highest power s to the power 4 and then if this is even, then we write all the coefficients having even power of the s in descending order. So, one coefficient of this, then 18, power s to the power 0, that is 4, the constant term. Then we write in descending order all the powers of the s to the power 2, s to the power n, and s to the power 0. Here the coefficient of s cube is 8 and then s to the power 1, that is 16. Now, we will put 0 because there is no any term. Here we multiply these two terms and subtract the multiplication of these two and divide by this. So, in this case we will get 18 into 8 minus 16, and this will be, and divide by 8, this will be 16. At this place 8 with the 4 and 1 0 and divide by 8. So, this will be 4. You can directly write 4 if here is 0, because this has to become 0 and we are ultimately dividing by this term only. So, we can direct copy it here. Here we have to multiply these two terms, subtract this and divide by this. So, 16 into 16 minus 256 minus 8 into 4, 32, and divide by 16 and this will be 14. This term you can write directly here, because this multiplied by this minus 0 divided by 16, this will be 0. Here this multiplied by this, so this will be 4. So, the second Routh stability criteria is there must not be any sign change in this column. As many sign changes are here, the same number of poles are lying in the right half of the S plane. In this case, there is no any sign change in this column. So, there is no pole in the right half and the system will be stable. Let us solve another example with a different case. The characteristic equation P of S is given by S to the power 5 plus S to the power 4 plus 2s cube plus 2s square plus 3s plus 15 is equal to 0. So, if you construct the Routh array, so the highest power is S to the power 5, this is odd number. So, I will write all the coefficients having odd power of the S, and this will be 1, the coefficient of S to the power 3 is 2 and 3 here. In descending order, I will write S to the power 4, S to the power 3, S square, S and S to the power 0. The coefficient of S to the power 4 is 1, the coefficient of S square is 2, and S to the power 0, that is the constant term, is 15. Here 1 into 2 minus 2 divided by 1, so this will be 0 minus 12, and the term here I will get is 0. So, if we are getting a 0 in the first column, we will replace it with a very small positive number and further we will proceed our calculation. So, you will replace it with the small positive number, that is epsilon. Here I will get 2 epsilon plus 12 by epsilon, and epsilon is a very small positive number which is tending to 0. Here I will get 15 into epsilon divided by epsilon, so it will be 15. If epsilon is tending to 0, this term will tend to infinity. If limit epsilon tends to 0, this will be infinity. So, this will be tending to plus infinity. The term that I will write here is the minus 12 time 2 epsilon plus 12 by epsilon minus 15 epsilon divided by the whole divided by this 2 epsilon plus 12 by epsilon, and if I solve it, this is minus 24 epsilon minus 144 minus 15 epsilon square by 2 epsilon plus 12, and if epsilon is tending to 0, this will be minus 12. So, I can write here directly minus 12. and here I will get 15. So, in this case the first column, this is a positive number, and here is one sign change, from plus infinity it is becoming minus 12, and then again from minus 12 it is becoming 15. There is 2 times sign change, means the transfer function having characteristic equation this P s will have 2 poles in the right half of the S plane, and if there are 2 poles in the right half, means the system is unstable. Let us solve another example. P of s to the power 6 plus 2 s to the power 5 plus 8 s to the power 4 plus 12 s cube plus 20 s square plus 16 s plus 16. If I construct the Routh array, the highest power is to the power 6 and this is even. So, I will write all the coefficients having even power of the s in descending order. So, this will be 1, 8, 20 and 16. Now, the coefficients of s to the power 5 in this array 2, 12, 16. Here I may or may not write 0. So, for the s to the power 4, if I multiply 8 into 2, 16 minus 12, 4 divided by 2. So, this will be 2. 2 into 20, 40 and minus 16, 24 divided by 2. So, this will be 12, and here I can write the 16 directly because here is 0. Now, for the s to the power 3, I will get this, both numbers are same. So, this will be 0, 24 minus 24 will be 0, and similarly here also 2 into 16 minus 2 into 16 will be 0, and obviously here will be 0 if I write. So, here all the terms are 0. In this case, we form an auxiliary equation, and the auxiliary equation will be the row in which we are getting all the coefficients 0 just before that row. So, in this case our auxiliary equation will be A of s. Let me write it in on another board. So, the auxiliary equation will be two s to the power 4 plus 12 s square plus 16. After differentiating this auxiliary equation and whatever the coefficients I will get, I will replace this row containing all zeros with those new coefficients, and if I write d A of s ds, I will get 8 s cube plus 24 s. So, the coefficients I will write here 8 and 24, and I will proceed by Routh array. The coefficient that I will get here will be 6. If I calculate, I will get 6, and here I will copy this 16 directly because here is 0. So, this will be 16 for s to the power 1. So, here I will get 24 into 6 minus 16 into 8 divided by 6, and this will be 16 by 6, and here is obviously 0. for s to the power 0, I will get 16. So, in this case all the coefficients are positive, but when we get all 0 in a row, this means we have few poles on the imaginary axis, and in this case we have to check whether they are double pole or not. If they are double pole, our system will be unstable, we have seen earlier. So, in this case we have auxiliary equation 2 s to the power 4 plus 12 s square plus 16, and we will have to find all the roots of this equation, whether they are double or not. This is a fourth order equation, but it is very easy to solve because there is no s cube term, and if I replace s square with the t, it will become quadratic, and if I solve it, I get s is equal to plus minus 1.12 I and plus minus 2.17 I. If I plot it, it will be something like this, 2 complex conjugate and one pair somewhere here, 2.17 I minus 2.17 I minus 1.12 I. So, there is no any double pole on the imaginary axis, means our system is marginally stable, it is not unstable. Let us see another example. The characteristic equation is given by 2 s to the power 5 plus s to the power 4 plus 4s cube plus 2s square plus 2s plus 1. In this case, the Routh array, if I form starting from s to the power 5, 2, 4 and 2, s to the power 4, 1, 2 and 1. The coefficient in this row s cube, 4 minus 4, it will be 0. Here 2 minus 2, again this will be 0. So, again we are getting all the terms in this row 0. So, we will have to find the auxiliary equation, and then we will have to find the new coefficients. Suppose I write this auxiliary equation with A of s, this is S4 plus 2s square plus 1, and d of s by ds will be 4s cube plus 4s. So, I will have to replace this 0 in this row, we are getting all the 0. This is 4 and this is also 4. Now, for the s square, we will get 8 minus 4, that is 4 divided by 4, that is 1, and here I will get 1. For s, I will get 4 minus 4, this is 0, and this is already 0. So, again we are getting all 0 in this row. So, I will have to form one more auxiliary equation. So, if I write this A1 of s, now I will get second auxiliary equation A2 of s, and this is s square plus 1, and if I differentiate it, dA2 of S by ds, I will get 2s. So, I will have to replace this 0 with 2, and now for s to the power 0, I will get 1. So, all the coefficients are positive, but we have to check whether there is any double pole on the imaginary axis or not, and for this we will have to find. So, we have two auxiliary equations. The roots for this equation we get, that is already the root of this equation. So, we have to find the root of this equation only, of the A1 of S. So, if I write s to the power 4 plus 2s square plus 1 is equal to 0, if I replace s square with the new coefficient and if I solve it, I will get two roots. S is equal to plus minus I, and the second root is also plus minus I. So, if I write it on the complex plane, the real part of S, imaginary part of S. So, I have two roots here and two roots here. So, we have double pole on the imaginary axis and my system will be unstable. If you remember, its response was t sin t. It will look something like, if this is my t, its response will be something like this, and system is unstable. Thank you very much.